educational satellite television programs.
Hello, teacher. Hello, students. Welcome to today's lesson on fluid dynamics. Previously, we were introduced to the Bernoulli principle, as well as some examples of how it works. We also defined laminar or streamline flow as well as turbulent flow. Today, we will be looking at laminar flow in greater detail. Let us begin. Students, in our last lesson, we defined laminar flow as a type of flow in which the velocity and pressure remain constant. If we measure how much volume of liquid is crossing a given point per unit of time, we are determining the rate of flow. We have seen how laminar flows can increase velocity in an object, but unless you keep pushing an object, it will slow down as it faces air resistance. Air resistance opposes motion, and, in general, larger surfaces travel more slowly through the air. To fight this resistance, we use a process called streamlining. Students, let us test our understanding of this idea. In cars, streamlining is done to improve the performance or speed of the vehicle. Here, we see two cars. Which one of these do you think is the faster vehicle? Why do you think this is? Take a moment to think about it and write your answers down.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Welcome back, students. I am sure this question was not too difficult for you. The answer is the car on the right. Notice the difference of shape of the two vehicles and try to relate it to what we learned about Bernoulli's principle. The car on the left is covered with angular, flat edges which impede the flow of air. The car on the right is streamlined, meaning it is shaped in a way that allows the air to flow more freely around the vehicle. This means that there are fewer barriers to create air resistance. The edges are rounded, and the chassis of the car is much closer to the ground. The car on the right goes significantly faster as a result. The process of streamlining is also applied to boats. The curved edges of a boat allow the flow of water to pass more easily around its body. Sails can manage the flow of air to affect their direction and speed. Incidentally, most aquatic animals are also streamlined. Dolphins and whales, for instance, have body shapes that allow them to travel more quickly and efficiently through liquid flows. It is extremely important that we streamline airplanes. Successful flight requires a delicate balance of airflow to maintain a steady path. We use rudders on the wings of a plane to occasionally oppose airflows to create resistance necessary for the plane to descend or land. An airplane has a cylindrical body shape. If it had a rectangular body shape, the combination of air resistance and weight of the vehicle would never allow it to take off. In the study of fluid dynamics, we often use the equation of continuity, which states that the volume flow rate of an ideal fluid flowing through a closed system is the same at every point. It is expressed as flow rate equals volume divided by time. We use the equation of continuity to examine the rate of flow in pipes, tubes, and ducts with flowing fluid or gases. We also use it to examine the processes in power plants, computer networks, and semiconductors. It allows us to measure how successful our streamlining is relative to the ideal result. We can test the streamlining of fluids using tools such as a Venturi meter. A Venturi meter uses a length of tube with one or more wide sections and at least one narrow section. Pushing fluid through the wide end and into the narrow end creates a jet effect. This jet effect has been named the Venturi effect. The Venturi effect increases the fluid's velocity as the pressure on it increases. A Venturi meter allows us to monitor the difference in pressure between the wide and narrow portions of the tube. The Venturi effect can be observed in many common objects. Using a garden hose, we can demonstrate the Venturi effect simply by turning on the pressure and putting a thumb over the spout. This creates a jet effect consistent with the description of the Venturi effect. Students, let us do an activity. How many objects can you think of that demonstrate the Venturi effect? Please write them down now.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Welcome back, students. I trust that you were able to come up with a few examples. The Venturi effect can be observed in many instances. One example is a perfume bottle. The mechanism on the bottle forces the liquid through a narrow tube. When the fluid leaves the bottle, it appears as a jet. This is also similar to an aerosol or spray can. The lead pipe of a trombone also shows evidence of the Venturi effect. We blow air from the comparatively wide tubes of our lungs into the narrow end of a trombone to create an airflow that travels through the tube. A jet of airflow travels through the tube, and the volume of air and air pressure passing through it will create changes in timbre as the air leaves the instrument. If you have an example that demonstrates the Venturi effect similar to the ones we have presented, you are showing great understanding. Good job. Students, this concludes today's lesson on the characteristics of laminar flow. We have examined some concepts such as rate of flow and streamlining. We have also introduced the Venturi meter and Venturi effect as a means to study the rate of flow of fluids. Until next time, thank you, teacher. Thank you, students.